Hi guys, this is Sadaf, and today I'm gonna talk about how to make a buffer based on given pH values. As we can see, I have 3 assigned pH values right here, and to make a buffer, we have to follow a series of steps. Starting off, we have to choose a buffer that has a pKa closest to the pH needed. Step 2 would be to use Henderson-Hasselbalch equation to figure out the ratio of our acid to conjugate base. Step 3 would be to calculate the mass or volume of the solution needed to get the ratio of our concentration of acid plus concentration of base from step 2. That all sounds a little confusing, but as we go over the steps and I actually get to show the math, it will make a lot more sense. Okay, starting off with choosing a buffer. Now, these tables up here are tables that Uting is going to provide for us, and we're going to use these tables to look at our acids and the pKa's. So I'm given 1.30, 7.30, and 10.60 as my pH values. Looking at the side right here, I can see that the closest pKa value to my 1.30 pH value is oxalic acid with a pKa of 1.42. Same with 7.30, I can see that 7.20 is the closest value to my pH. And then 10.60, 10.33 is the closest value in this table to my pH value. Okay, so for the sake of clarity, I went ahead and color-coded everything. I also jotted down the acids and the conjugate bases. Now, figuring out the conjugate bases are quite simple. You can either look it up or just take one of the hydrogens away from the acid because they dissociate. And some of the acids do dissociate twice, just like oxalic acid on my list. But we're only concerned with the first dissociation because of the pKa value. So the second one does not really matter in this situation. Either way, moving on, we need to figure out which method to use for each one of these pH values and acids. The 3 different methods are solid solution, solution, and titration. And so of the 3 methods, 2 of them require the acid to have a conjugate base. And those 2 methods are solid solution and solution. Also, if you have an acid without a conjugate base, your only choice for one of the methods is titration. And there is a strong base available on this list provided by Uting to use, which is sodium hydroxide right here. Also, some compounds provided are only available as a solid, and in that situation, you have to use a solid solution method. And some compounds provided are available as a solid and solution. For those ones, you can decide and it's up to you. And for extreme ends of pH that are like super acidic or super basic, titration is the best method, which is why for my 1.30 pH, I picked titration. And on this list, I have sodium oxalate, and I can use the strong base that was mentioned earlier, sodium hydroxide, to perform my titration. And then for my 10.60 pH of hydrogen carbonate ion and carbonate ion, those 2 are very conveniently both provided as a solution. So we can see sodium carbonate and sodium hydrogen carbonate. And also, we know that sodium is neutral, so we ignore them. They're neutral when dissociation happens in pH levels, so we just don't care about it, and we only look at the carbonate and the hydrogen carbonate, which are the two things that we need. And that only leaves us with our solid solution, and I went ahead and picked sodium dihydrogen phosphate monohydrate and sodium hydrogen phosphate for my 7.30 pH. Now that we have everything we need, we can move on to our calculations. So we want a 60 milliliter solution because that is the max amount that Uting has recommended for us to use. So therefore we're going to stick to 60 milliliters. We want that as a pH of 73.0 buffer. We have 0.10 molar sodium hydrogen phosphate and solid sodium dihydrogen phosphate monohydrate. I wrote down my acid and my base and where I derived them from, and then we can just move on to the calculations, which, as I mentioned earlier, is using the Henderson law to figure out the ratio of our acid to conjugate base. So now I'm gonna write down my formula, which is pH is equal to pKa plus log of conjugate base over acid. And we know that our pH is 7.30. It was given to us, and from our table we picked the closest pKa value, which was 7.20, plus log of our conjugate base, the concentration of the conjugate base, and the concentration of our acid. Now we need to solve, and we obviously subtract the 7.20 from over here and 7.20 from here. This crosses out and we are left with 0. Left with 0.10. That's equal to our log of conjugate base over acid. Now we need to get rid of our log. How do we do that? Base 10. So we have our base 10 to the power of 0.10 is equal to, got rid of that, our conjugate base over acid. So we have conjugate base over acid, and it's equal to 1.2589. And for the sake of sig figs, we're gonna round to 3 decimal places. And we have 1.26 over 1 as a ratio of conjugate base to acid for our 7.30 pH. Okay, now that we have our conjugate base to acid ratio, we can go ahead and find the moles of each compound used. And to do that, we start off with the moles of our conjugate base, which is HPO4 2- monohydrogen phosphate ion, and we can set this equal to our volume of base, and we convert it to milliliters. So I'm going to divide that by 1,000 liters. We multiply that by our 0.10 given value. Now once you go ahead and solve this, you should get 0.0001 times our volume of base. Now, from the ratio, we've already derived the fact that our moles of conjugate base over mole of acid is equal to 1.2589. We can just go ahead and rearrange this so we can solve for the moles of acid, and when we do that, our moles of acid is equal to moles of our conjugate base over 1.2589. And as you can see, we already know that the moles of our conjugate base is this equation up here. So we just related these two together, and we also now can use substitution to solve for each one. To make it easier on myself, I am going to assign a value to my base, a volume, to my base, because this is something I can choose. It's not set. It doesn't matter how much of it I use, as long as it's something that I could add on to later and it won't go over my 60 milliliter limit. Because of that, I'm just going to go with half of it, and I'm going to just go with 30 milliliters. And so from there, I can say that the moles of monohydrogen phosphate ion, which is my conjugate base, is equal to 0.0001 times my 30 milliliters. And just one more time, I got this from right over here, and this is equal to 0.0030 mole. Now to solve for moles of dihydrogen phosphate ion, we have this equation right over here, where our moles of acid is equal to moles of our conjugate base, which we just calculated as 0.0030. This is molarity, and we divide that by this right here, 1.2589, and that's equal to 0.00238 moles. Okay, now that we are done calculating for the moles of each compound, we can move on to calculating the mass of the solid. The solid that we chose earlier from the table was sodium dihydrogen phosphate monohydrate, and the molar mass is 138.00 grams per mole. Now we know that mass is equal to moles times molar mass, and the moles we just calculated earlier, it's this value over here, 0.00238 moles, and that's times the molar mass, 138.00 grams per mole. Simply multiply that and you should get 0.32844, which is about 0.33 grams. Now we are done with all the math. We simply just have to jot down a couple of steps to ensure that we know what to do in lab. And those steps can consists of measuring 30 milliliters of our 0.10 molar sodium hydrogen phosphate solution that we got from the table above over here, so it is available in class. And then we can weigh about 0.33 grams of solid sodium dihydrogen phosphate monohydrate, and you can aim for anything above or below of 0.005 grams as long as it's close to that value. And then the last step is just to combine the two, mix them, and you can also dilute it by adding water to reach the 60 milliliter goal, just because our goal initially was 60 milliliters. Moving on, I'm gonna start off with my solution of 10.60 pH, and I wrote some directions for myself. So again, I want a 60 milliliter solution of a pH of 10.60 buffer. We have 0.10 molar sodium hydrogen carbonate and 0.10 molar sodium carbonate. And again, I'm gonna use Hasselbalch equation, which is written right over here, and I also wrote down what each one is and what they mean. So I'm just gonna go ahead and plug them in. So my pH is 10.60, pKa is 10.33, plus the log of my base, which is carbonate ion and hydrogen carbonate ion, but I'm just, for the sake of simplicity, just write acid and base and acid, sorry. Again, simply just subtract, try to get the variable, which is this right here, all by itself. 0.27 is equal to the log of our base over acid. Again, we simply just take the base 10, so we have 10 to the power 0.27, which is equal to our base over acid. And this is equal to about 1.862, and we're gonna go with our sig figs, but I'm just gonna write down the whole thing in case I need to use it once we move on further down. Either way, the ratio of our base to acid is about 1.86. Now that we are done with that step, we need to move on and relate our concentration to volume. From the series of steps that I stated over here, we can see that because both of our stock solutions have the same molarity, the concentration ratio is equal to the volume ratio, and therefore we have our volume of base is equal to 1.86 times the volume of our acid. Now we need to solve the volumes, and we can do this by using substitution. So we have our volume of acid plus our volume of base is equal to 60 milliliters. And this is just a value that I chose, so whatever value that you end up going with, feel free to replace it with that value. Now we can substitute this value into this equation right here to solve. So then we are going to end up with 1.86 times volume of our acid plus volume of our acid, and that's equal to 60 milliliters. And from here have 2.86 times VA, that's equal to 60, divided by 2.86, divided by 2.86. This crosses out, and we are left with VA is equal to this divided by that, which is 20.98 milliliters. And from here, we can just go back to our formula over here for our VB. That would be equal to 60.0 minus 20.98, which is equal to 39.02 milliliters. We can also round this for practicality, which will be, so the volume of our acid, which is sodium hydrogen carbonate, it will be 21.0 milliliters. And for our base of sodium carbonate, we can go to 39.0 milliliters. So we round this one down. And then this one's pretty much done as well, and we just have to come up with a series of steps to follow. And we can start off by measuring approximately 21.0 milliliters of our 0.10 molar sodium hydrogen carbonate solution, and using appropriate lab equipment. We can then measure approximately 39.0 milliliters of the 0.10 molar sodium carbonate solution, combine them in a beaker or a flask, and you can also use DI water if the solution is a little off of the 60 milliliters. And you should be able to stir, check the pH if needed, and then if there's a situation where it is off a little, you can always add small amounts of sodium carbonate to lower the pH. Next, we have the very last one, titration. And again, I'm going to go with 60 milliliters of a pH 1.30 buffer. We have 0.10 molar oxalic acid and 0.10 molar sodium hydroxide. I went ahead and wrote down my formula again and what each of the values represent. So I'm just going to go ahead and plug those in. My pH is 1.30, pKa is 1.42, plus log of my conjugate base, the concentration of my conjugate base over the concentration of my acid. And we are solving for the log of conjugate base over conjugate base of acid. Again, just gonna subtract 1.42 from here, 1.42 from here. This cancels out. 1.30 minus 1.42 is negative 0.12. That's equal to our log of conjugate base over acid. Log base 10 again, so we take base 10, this crosses out, and we will have 10 to the power of negative 0.12. It's equal to our conjugate base over our acid, which is equal to 0.758578. Sig figs right here. So the ratio of our conjugate base to acid is about 0.7586. Now that we have the ratio, you can use a pH meter to determine the endpoint. Ratio was achieved when the meter reads 1.30. How we go about this is we use to make 60 milliliters of the final buffer, we start with about 60 to 80% of the solution, so there's a room for the addition of sodium hydroxide. So we're just going to start with 40 milliliters of our 0.10 molar oxalic acid. And now we need to find the initial moles of our oxalate acid, which will be equal to 0.040 liters times 0.10 moles per liter, which is equal to 0.004 moles. Based on this, we know that there's plenty to create the buffer and ensure the final volume doesn't exceed our 60 milliliter after the addition of sodium hydroxide. And moving on, we need to approximate the volume of NaOH. So how much NaOH will we be adding to this titration? So I'm going to have X equal to moles of my sodium hydroxide added. I'm going to have X divided by 0.004 minus X equals to 0.7586. And this is the ratio that we just calculated up here, and this also comes from the value over here. So we just go ahead and solve this. We got X is equal to 0.7586 times 0.004 minus X. We are going to distribute in 0.0030 minus 0.7586x. We add this to both sides. This crosses out and we will have x plus 0.7586x equal to 0.0030. We add them, we get 1.7586 0030 divide crosses out. X is equal to 0.0017 moles of NaOH. Now we can also convert this, so we have volume of 0.10 molar sodium hydroxide, which is equal to 0.0017 moles divided by 0.10 mole per liter, which is equal to 0.017 liters or 17.00 milliliters. And that's it. That's everything you need to do to be able to solve or make buffers out of given pH values. Thank you.